All right, today we're going to talk about B trees, but before we go into that, make sure everyone who's in class that you go and sign up and create an account on Overleaf. Just create the account, and then you should be given a little menu about being able to create a PDF, and we're going to take it from there. Yeah. So, and for those of you online, you're going to need to do this to follow us today. So B trees. So what type of tree have we talked about so far?
Binary trees.
Binary trees.
Binary search trees.
Binary search trees, that's good. And what's their defining feature?
Which ones? All of them?
No, binary trees.
Binary trees is that you have login time for search and like everything else.
So how many, good morning.
Morning.
How many children do you have?
I have none. Right?
2. Thank you, Matt. But a binary tree is 2 children.
Yes.
A singly linked list, you can think of having 1 child. Binary tree is 2. So a B tree, how many do you think it has?
8.
8?
4.
4? Okay, guess what it is.
17.
So in computer science, we'll do 1, we'll do 2, and then after that, we'll just parameterize it. So it has in children, and you just define what in is when you instantiate the B tree. Sorry. Why would we want to do that? Yeah. So it may have 100
One
children.
parent and then just children.
Yeah, maybe 100 children, maybe 5 children, maybe 1,000 children,
Then do you make another?
and then each of those children can have another 1,000 children. Why would we want to do this? Why would we?
Storing a lot of data, I guess.
Well, in a single linked list, how long did it take to search it? O(n), yeah. And then a binary search tree, assuming it was balanced, took how long?
Login.
Log log base 2 of n. So, but if you have 1,000 children and you want to find something, now what is the search complexity?
Log base 1,000.
Yes, log base 1,000 of n, which is significantly faster. And we'll see that in a moment. So yes, we'll go ahead and talk about B trees. For those of you who just came in, go to overleaf.com and create an account. We'll be using it today. All right, a little more motivation. B trees are really used for databases. Most databases have some sort of B tree architecture or data structure in the back end. It's great for indexing large data sets that can't be stored in memory. They need to be stored on the hard drive or some other storage system that can't be main memory. Unfortunately, this requires a little different approach. Now, these we haven't talked about solid state drives yet. Those are definitely faster, but the same problem still exists because main memory is still significantly faster. But these are going to talk about the standard spinning disks because the numbers are a lot easier to recognize why it's so important. So if you have a 3600 RPM, it occurs, what is it, 1 revolution, 1/60th of a second, or 16.7 milliseconds, which is incredibly slow. In other words, your computer can do about 200,000 instructions or operations, additions, in the time it takes the disk to revolve once. If we used an AVL tree to store 20 million, we would have a very deep tree. Actually, how deep would it be? Oh, about 24. There we go. Log base 2 is 24, which means in order to find something, you would have to go to the hard drive 24 times in order for you to find one element. And that would take 0.2 seconds. And if this is a server that's servicing thousands of these things, 1,000 times 0.2 is what, 200 seconds would be the average response rate. Anyone want to wait 200 seconds for their web page to load? You don't want to, Matt?
No, that's too long.
That's too long, right. Okay, so obviously the AVL is not going to be sufficient here. So what we do instead is add more branches to reduce the height of the tree. All right, so we don't have the numbers here, but if it was log base 1,000, what would that be? 3? Yeah, it'd be about 3 instead of 24. So a significant jump. All right, everyone understand why we do B trees? Good. So let's go to the official definition, at least the ones provided. A B tree, by the way, there's B plus tree and B star tree. There's all different types of trees. We're just going to talk about the basic B tree, and if you they're basically the same thing with a couple different additions to for performance in certain situations. So just keep in mind that when someone talks about a B tree, they may be talking about some other type of tree. But we're just going to talk about the standard B tree for now. And don't get the word B confused with binary as well, because there's linked list, binary tree, and B tree. Those are all three separate things.
What does the B stand for, B tree?
That is a great question. I've never looked that up. I've never looked that up, yeah. What's it stand for, Matt?
Okay. This was unknown for a long time. All right.
It was unknown for a long time.
Yes.
On Wikipedia, it says it's called a B tree because it's just a binary search tree that can have more children.
Wow, they said they were working for Boeing at the time.
Oh, so it's actually a mystery.
Another Bayer was the senior author, so they're just not sure.
Someone probably called it that, it stuck, and then no one now remembers why. No one cares. We just call it B trees. I guess we could have called them D trees, but we call them B trees. All right, so there's 5 rules. Well, there's technically a 6th one because the number n should always be odd. So the way should always be odd. So if you don't do 1,000, order 1,000, you do 1,001. And this will make some sense when you start looking at all the numbers. So first rule, the number of keys in each non-leaf node is 1 less than the number of its children. And these keys partition the keys in the fashion of a search tree. In other words, 1 less than the number of its children. So if you have 5 children, you need to have 4 entries at your current level. So you need to think about this with a binary tree. Oh, I don't have my camera. With a binary tree, the root would only contain 1 element, and then you would have 2 children. But with a B tree, since you're going to have multiple children, you need to figure out a way to basically divide it up properly. Let's see if I can load this camera up real fast. Yeah. All right. Hopefully red will show up today. All right, give me some numbers.
18. 2.
4?
25.
What?
25.
25.
65.
65. 41. Making my life difficult. All right, we're going to do, you said 41?
Yeah.
Good, so we'll do, let me go ahead and add a couple more numbers. Just so this makes a little more sense. That's a 41, even though it might be hard to see. We'll put a 10 over here. Oh, there's 81 right here. Okay. So a little different structure now. The root has 2 values in it. And what the first rule is saying, if you have 2 values, then you must have exactly 3 children. Or in other words, if you have 3 children, you must have 2 values. If you have 5 children, you must have 4 values. If you have 10 children, you must have 9 values. And the reason for this, if you look at it pictorially, you need to know to the left of the first element what there is, to the right what's in that one, to the next to the right what's over there, so forth and so on. And if you, hopefully you can see that you need 1 more child than the number of elements you have in order to break this up evenly, because the idea is that if you're at 18, or you're looking at this value and you're looking for 25, you know that 25 is between these two, so you know to jump down to the middle. Okay. Any questions on that? Rule 1? No questions? I'll make more sense in a minute. All right. Rule 2, all leaves are at the same level. That's what we have in this picture right here. All these leaves are at the same level or the same height. If you had a more complicated one, you couldn't end it somewhere else. All your leaves have to be at the end. All leaf nodes except the root must have at least m divided by 2 children. That's going to make a lot more sense when we have a more complicated B tree, which we'll get to in a minute. That's just a way to doing balancing. The root is either a leaf or it has 2 to m children. In other words, the root cannot have just one child. And a leaf contains no more than m minus 1 keys. All right. And m should be odd. Okay. So let's see if we can do some good examples. Oh, here's a good one. Of order 5. Notice that all the leaves are at the 3rd level, because you go 1, 2, 3, and 1, 2, 3 down here. And then what was the other rule? All leaves, all non, except the root have m divided by 2 children, or at least have at least m divided by 2. So 5 divided by 2 is technically 2.5, but since it's an integer, you round down, which makes it 2. So everything but the root has to have at least 2 children, or non-leaf must have at least 2 children, which is also the case here. Right, it's either a root or has 2 or more children. Obviously it has at least 2 right here. And then a leaf can contain no more than m minus 1, so no more than 4. So right here is 4, that's our largest. All right, so this is a B tree. We're gonna have to do some examples to figure out, to see this more in action. Does it actually show it? Great. So we're gonna start with an empty B tree, and we're going to add order 5. We'll add 1, 12, 8, 2, etc., etc. The first 4 are easy because you just put them into an array. Note that your B tree node is actually an array of integers, or vector if you prefer.
I have a question.
Yes.
So we have order 5, which determines that we can only have up to 4 in each one.
Up to 4 in each one, up to 5 children.
So, how did we get order 5? Is that given? We have to choose that?
Right. When you create your B tree, you're telling us you create it with a certain order. Maybe you want one of order 5, order 10, order 1,000, etc. Yeah. That's just something you parameterize. Hopefully, you'll see once we're done that there's a little bit of a trade-off there. But yeah, that's something the programmer says. Now, if we put the 5th element, namely the 25, in, that would violate condition 5, which is saying that you can't have more than n minus 1 elements in each node. So we need to basically promote, morning Jonah, go to overleaf.com and create an account. You probably have one from last year, so sign in. Okay. So we can't have 1, 2, 8, 12, 25 because it's order of 5. So we need to do something else. And what we do is, since the 5 would go right here, we take the 8, promote it to the new root, and have the left go to 1 and 2, and have the right go to 12 and 25. Like that. Anyone see that? You can add, let's see, they add 6. 6 goes right over here. 14 gets shoved in the middle, and 28 gets added to the end. But when you add 17, where's the 17 going to go?
The 1, 2, 6.
17.
Go up with 8.
You would, okay, right. You would put it originally between 12, 14, 25, and 28, but then that would violate rule number 5, which you can only have n minus 1 children. So you promote the one that's in the middle, which just happens to be the 17 in this case. It gets promoted up. The one in the middle goes to 12 and 14, and to the right of the 17 goes 25, 28. Like that. Any questions so far? Let's see, so we have 7 right there, 52 goes over here, 16 goes in the middle, and 48 goes over here. What gets added next? All right, 68. Everyone ignore that happened. Where would the 68 first go?
After the 52.
After the 52. And do we have a problem?
Yes.
Yes. What is the issue?
There's 5.
Right. Violate condition 5. So what do we do?
Promote 48.
Promote the 48. So the 48 goes up, and then we split along those two. So the 48 gets promoted. Let's see, in between you get 25. Well, the 48 gets promoted, and then you would have this arrow from here pointing 25, 28, and the one after the 48 going to just 52, which is fine. All right. Let's see. Promoting 48 to the root and adding 3 causes us to split the leftmost leaf. Yeah, if you added 3 over here, you would have the same problem, so that would have to be promoted as well. That's what they're showing. And then, let's see, 26 right here, we're still good. 29 goes, right, same thing, we're good. 53, we're good. And 55, we're still good. All right, and then what comes next? All right.
Well, M root can't add anymore, right?
Right, so we add a 48, or 45, right? 45. You would add 45, would go over here. Why is the 45 going to this node?
So that's the 48, or the 13.
All right, everyone see that? Great. Causes a split, which promotes the 28 up. But now we have another issue. What's the new issue?
The root's too big.
So what do? We split the root. So what's going to get promoted in the root? The 17. When the dust settles, it's something like this.
So it's kind of like you start from the bottom up.
Yeah.
So it kind of feels like, but not really.
Yeah, that's what you do. Bottom up. You gotta figure out where it goes. It goes into a leaf. Notice you're always adding to a leaf, and then you're coming back up and fixing things as problems arise.
So in this diagram, is the 17 pointing at the 8 or at the?
The 17 is pointing to the array of 3, 8. Right. These are all arrays or vectors. Any questions yet? Nope. Good. All right, so inserting, we went through pictures. Attempt to insert into the leaf. You always insert to a leaf first. If there are no issues, you're done. Everyone's happy. If there would result in the leaf becoming too big, split the leaf, promote the middle key to the parent. If that were to result in the parent being too big, split the parent again, promote the middle key. And you have to do this all the way up to the top because you might be splitting for a long time. And if necessary, the root is split into 2 and the middle key is promoted to the root, making the tree 1 level higher. Now notice, that's why the root can be 1 element, because you have this situation where you just want to promote the 1 element to the top and you have a new root. So that definitely can occur. But otherwise, each of the non-leaves are going to have at least m-2, the floor of m-2 number of elements in it. Okay, excuse me. All right, I'm going to take a break here.